Hello everyone. In this video we are going to cover lesson 12-2 on implementing a graph abstract data type. Practice for this lesson include implementing a graph in two different ways. We're going to talk about adjacency matrices and we're going to talk about adjacency lists. These are two different ways you can implement a graph. We're going to compare the different implementations, and then we're going to implement common graph traversal algorithms, including breadth-first search and depth-first search. As we have seen with the previous abstract data types, there are several ways to implement a graph abstract data type. So in this lesson, as I said earlier, we're going to cover two different implementations. Let's start first with adjacency matrices. An adjacency matrix is a two-dimensional matrix where each vertex, v sub I, is assigned row I and column I. If two vertices, v sub I and v sub j, are adjacent, then there is a 1 in the ith row and the jth column in the matrix. Otherwise, a 0 is placed in the respective row and column, indicating that these two vertices are not adjacent. So the best way to learn is to look at an example. So here's the same example graph we used in our previous lesson on the high-level overview of graphs. So here's an adjacency matrix for the above graph. So vertex number 1 in the first row and the first column, vertex number 2 in the second row and the second column, and so on and so forth until we have the sixth vertex associated with the sixth row and the sixth column. So if two vertices are adjacent, then we will have a 1 in the row and column representing each one of those vertices. So for example, 1 and 2 are adjacent. So row 1 and row 2 has a 1 representing vertex 1 is adjacent to vertex 2. And then also vertex 2 in row 2 and vertex 1 in column 1 are adjacent as well. So these are, this is not a directed graph, so these are bidirectional. 1 is adjacent to 5 and 5 is adjacent to 1. So we have this symmetrical looking graph here. Note that by definition, a vertex is not adjacent to itself. We could represent this adjacency matrix quite simply using a nested list as such, or using a NumPy ND array. To find out if two vertices v sub I and v sub j are adjacent, we just need to look up if there is a 1 in the matrix at position I, row I, and column j, which is a constant lookup. This is constant time complexity. So in terms of time complexity, this is quite nice, quite easy to work with, and logically it makes sense. But the size of this matrix is the number of vertices squared, which can be quite large if you think about some social media graphs, such as friends in a Facebook group, for example. Adjacency matrix with the majority of the entries 0 is said to be sparse and is not an effective use of memory. So in general, many of our graphs will not be fully connected, meaning our vertices are not going to be connected to every other vertice. So we're going to have a lot of zeros in our adjacency matrix, which can not effectively be a use of memory. So this shortcoming can be overcome with a sparse matrix representation, such as adjacency lists. So in this case, we're going to trade off space for lookup time complexity. So let's look at a sparse matrix representation, such as adjacency lists. An adjacency list is a list of vertices where each vertex has a list of adjacent vertices. Each vertex is in the list of adjacent vertices represents an edge. So let's take a look at our same example and see what the adjacency list implementation looks like compared to the adjacency matrix implementation. So an adjacency list for the above graph using Python dictionaries where the keys are each one of the vertices and the values are list of adjacent vertices. So for example, key 1 represents vertex 1. Vertex 1 is adjacent to 2 and to 5. So we see the value associated with key 1 is the list containing the neighbors 2 and 5. Let's take a look at another example. Vertex 2 is adjacent to 1, 5, and 3. So the key representing vertex 2 maps to the value of the neighbors of 2. Those are the vertices adjacent to 2, 1, 3, and 5. Now, let's take a look at the space complexity for adjacency lists. The size of an adjacency list dictionary is the number of vertices plus 2 times the number of edges. This is because each edge appears once in the graph but is stored in a list twice. So, for example, the edge between 1 and 2 is stored in the value associated with the key 1 and the value associated with the key 2. To find out if two vertices v sub I and v sub j are adjacent, we simply need to look up v sub I, so that would be the key I, walk through each item in v sub i's edge list, that would be the value associated with the key I, looking for v sub j. In the worst case, v sub I is fully connected to every other vertex in the graph, and this list traversal is big O of the number of vertices in the graph. But as I said previously, in many cases, the graph is not fully connected, meaning vertices are only connected to a few local vertices, not to all other vertices in the graph. So let's take a look at how we can implement an adjacency list using Python dictionaries and weighted graphs. In the case of a weighted graph, we need to store additional information for each edge, and that additional information is the weight, because this is a weighted graph. With the adjacency matrix, we either need to store an object, such as a tuple or an instance of a custom vertex class, instead of one, or we need to maintain a parallel matrix with this information. With the adjacency list, we can modify our keys to be instances of a custom vertex class. So this custom vertex class will store the name of the vertex, the key, and a dictionary of adjacent vertex names. So the keys in this dictionary are going to be the names of the vertices in the neighborhood of this vertex and the edge weights associated with those edges between the vertex and the adjacent vertices in the dictionary. The adjacency list is then a dictionary of vertex names, which are the keys, mapping to vertex objects, which are the values. We will define a graph class to wrap this adjacency list dictionary with our graph abstract data type methods that we presented in the previous lesson. The ability to add a vertex to the graph. So this will add a key for the vertex to our adjacency list, storing all of the vertices and their objects in this dictionary. We need to be able to add edges. In the case of a weighted graph, we will want to be able to add a weight or associate a weight with this edge. So when we add an edge, then we're going to update the dictionary of adjacent vertices in our vertex class. Don't worry for now if all of the dictionaries, well, 2 total, seem to be confusing. Once we look at the code, it will be clear which dictionary resides in which class. Next, we'll have our getters get a vertex by a vertex key. This will return the vertex object and get vertices to get a list of all of the vertices in the graph. This list of all vertices in the graph will actually just be a list of the keys in our vertices dictionary. And then implementation for contains to be able to add functionality for membership testing with the Python reserved keyword in. Okay, so let's take a look at our vertex class. So our vertex class is going to have an ID. This is our key, and it's going to have a dictionary of all of the vertices that this vertex is adjacent to. The keys of this dictionary will be the vertex keys, and the values will be the edge weight associated with the edge from this vertex to a vertex in the connected to dictionary. When we need to add a neighbor, this would be adding a new edge, for example, to our graph, then we'll have the key called neighbor, and if there's a weight associated with this for a weighted graph. So we'll add to our connected to dictionary this key, so this neighbor's key, and the weight associated with this edge. Implementation of the stir special method, just to print out that this vertex is connected to, and then a list of all of the vertices that it's connected to as specified in the keys of our connected to dictionary attribute. Get connections, this is going to get all of the keys of that connected to dictionary, and get ID and get weight are our getters. Our get weight, I should add some more detail here. Get weight accepts vertex key and uses that vertex key to index into the dictionary of the neighbors to get the weight between the current vertex self and the vertex connected to by this weight, or excuse me, by this edge. Now we're moving on to our graph class. In our constructor, we're going to initialize an empty dictionary. This is going to be our dictionary where the keys are going to be IDs of our vertices, our labels, and the values associated with each one of our keys is going to be a reference to an instance of our vertex class. And we'll simply keep track of the number of vertices in our graph for size purposes. Here is our string special method. It's going to print out all of the edges in the graph. Add vertex. When we add a vertex, we're going to increase the number of vertices in the graph, and we're going to create a new vertex with this key and add it to our list of vertices. Next, get vertex. We're going to make sure that this ID is in fact a valid key in our vertex dictionary. If it is, we'll get that vertex object associated with this key n. Otherwise, we'll return none. Contains is simply going to test, is this key representing a vertex ID is a valid key in our vertex list dictionary. To add an edge from F to T, F is going to be our starting edge, T is going to be our starting vertex, T is going to be our ending vertex, and cost is going to be the weight associated with this edge. We first have to make sure that F and T are in fact valid vertices in our vertex list, our vertex dictionary. Once we are sure they are, and if they're not, we'll make them, then we're going to add a neighbor to F, and that neighbor is going to be the vertex T, and the weight associated with that edge will be our cost parameter here. Get vertices is going to return the names of all the vertices in the graph from our list of vertices, our dictionary keys, and here is going to be our iterator functionality, and we're going to simply return an iterator over all of the vertex objects in our vertex list dictionary. Okay, so let's test out our graph class with a few examples. The example we're going to use is the graph with vertices 1 through 6 that we used up here. Now, this is not a directed graph and it is not a weighted graph. So what we're going to do when we add our edges is we're going to add them twice so that they're two-way. And we're also going to add a kind of dummy value for our weight. So there are 6 vertices in our graph. So let's just go ahead and make those 6 vertices in a loop from range 1 inclusive to 7 exclusive, and use our add vertex method to add a vertex with the key I, our loop control variable. Now, each edge is going to be two-way, so to represent this edge 1 to 2, which is not directed, we'll add an edge from 1 to 2 with a weight of 2. This weight here is dummy, it's arbitrary. And then we're going to add that same edge, but in the reverse direction from 2 to 1. That way, in both of these vertex objects connected to dictionaries, they know about each other. And we'll repeat this, and then we will print out our graph, which will print out a list of all of the edges in our graph. Now, let's talk about common graph traversal algorithms. So similar to trees, we need traversal algorithms that are going to start at a vertex and visit every vertex in the graph. The order at which we visit the vertices depends on the algorithm. In fact, we saw this with pre-order, post-order, in-order, and level order traversals of trees. The most common graph traversal algorithms include breadth-first search and depth-first search. So let's start with breadth-first search. The big picture idea of BFS, breadth-first search, is to explore the vertices in the closest neighborhoods first. BFS is going to start at a vertex and visit each vertex that is distance 1 away. Then it's going to visit each vertex that is distance 2 away until all connected vertices have been visited. And explicitly, we're going to make sure that no vertex will be visited twice. Now, some vertices have multiple adjacent vertices. For these vertices, a decision will need to be made about the order in which to visit the neighbor vertices. Consequently, a BFS traversal is not unique. So the BFS algorithm is going to make use of a queue to keep track of the vertices to visit, which we will call the frontier queue. Now, one thing I want to note is we've seen some similar functionality to this when we implemented a level order traversal. So the algorithm also tracks the discovered but possibly not yet processed vertices in a list, in a set, and we know what a set is. A set is a list without duplicates. So we call the set discovered set. So discovered, the vertices in the discovered set have possibly not been processed yet, so we need to keep track of whether we have encountered these vertices or not. So here's our algorithm for BFS. We need to have a starting vertex at which to start our traversal. We're going to enqueue that vertex to our frontier queue, and we're going to add it to our discovered set so that we know we have encountered this starting vertex before. While the frontier queue is not empty, meaning there are vertices in our queue to process, we're going to dequeue from the frontier queue into a variable called v, representing a vertex to process. We're going to process v. In the case we're going to implement today, this is simply going to be printing out the vertex key. Now, for each adjacent vertex, AV of v, if we have not seen AV before, meaning if AV is not in the discovered set, then we're going to enqueue AV to the frontier queue and add AV to the discovered set. Here is an implementation of breadth-first search, BFS, for a given graph G and for a starting vertex, start. Here's our frontier queue. I'm simply using deck from the Python collections module, and I'm going to restrict my deck such that I'm going to enqueue to the left side of the queue, and I'm going to dequeue by popping the right side of the queue. Discovered set is simply going to be a built-in set object in Python, and I started out with our starting vertex. So here are our 2 lines here associated with steps 1 and 2 here. So next, while our frontier queue is not empty, so while there are items in frontier queue, the length of frontier queue is greater than 0, we're going to pop our frontier queue to get the first item to process, because remember, we're going to visit all of the nodes in the closest neighborhood first. Those will be at the front of the queue. That will be cur v. Right here, I have print cur v. This corresponds to our step B here, process v. Now, for each adjacent vertex of cur v, we're going to get these adjacent vertices from the connected to dictionary. We have a method getConnections that's going to interface into the keys of that dictionary. If adjacent V is not in discovered set, which means we have not encountered this vertex before, then enqueue it in frontier queue and add it to the discovered set. So if I run this here, then I'm going to print out, starting with the first vertex. Okay, so let's look at our graph again. So starting with vertex 1, we're going to visit all of the nodes that are distance 1 away, so that would be 5 and 2, and then all of the nodes that are distance 2 away, 4 and 3, and then all of the nodes that are distance 3 away, that would be 6. And remember, BFS is not necessarily unique because we may end up visiting 5 before 2 or 2 before 5. The order at which we visit nodes or vertices in the same neighborhood, the same distance away, depends obviously on the ordering in our dictionary structure, which we know that's based on a hash table, and that is going to be unordered. Okay, so here we see our starting node first, neighborhood 1 away, 2 and 5, neighborhood 2 away, 3 and 4, and then the neighborhood that's 3 away, simply 6. Now let's talk about depth first search. The big picture idea behind depth first search is to explore paths as deeply as they go. So DFS, depth first search, starts at a vertex and visits each vertex along each path before backtracking on that path. And just like before, we don't want to visit a vertex twice. So once again, DFS, like BFS, traversal is not unique for similar reasons. BFS made use of a queue to keep track of the vertices to visit. DFS is going to make use of a stack. I love these two algorithms because they do make use of stacks and queues, which we are quite familiar with by now in our computer science and data analytics career. So we're going to have a frontier stack, which is going to keep track of the vertices to visit. And these vertices are going to be pushed onto the stack in a first in, last out manner. So the algorithm is going to also keep track of the discovered vertices in a set, just like we did in BFS. And we're going to see a lot of parallels in our DFS algorithm in our BFS, but instead of using a queue, we're going to use a stack, so that as soon as we push something, push a vertice on the stack, we're going to process it in order to follow our paths as far as they go until we have to start backtracking. Let's take a look at the depth first search algorithm. So DFS is going to make use of a stack to keep track of the vertices to visit, which we will call the frontier stack. The algorithm also tracks the discovered vertices in a set, similar to breadth first search, and we'll call this set discovered set, just like we did in BFS. So our algorithm is to push the starting vertex to frontier stack, and while frontier stack is not empty, we're going to pop it into a variable called v. If we have not encountered v before, meaning v is not in the discovered set, then we're going to process it, which in the case of our algorithm is going to be to print it. Then we're going to add v to the discovered set so that we know we've already processed this vertex. And for each adjacent vertex, a via v, we'll push a v onto the frontier stack. Let's take a look at the code here. So I'm going to use a deck just like I did for BFS, and I'm going to push items onto the end of my deck, the right-hand side, by appending. Here's our empty discovered set, and while there are items in the stack to process, go ahead and pop off from the far end, the right end of our deck, frontier stack, into curv. If curv is not in a discovered set, meaning we haven't processed it before, then we'll process it by printing it out, add it to the discovered set, and push all of the adjacent vertices to curv onto the stack. And if I run this, I get the order. So starting at 1, 1, 2, 3, 4, 5, 6, and then 5. And let's take a look at our graph again. So we start with 1. We follow a path as far as it will go before backtracking. So we go 1, 2, 3, 4, 6, and then we process 5, which is the only vertex that we have not processed yet, still on the stack. So let's talk about the algorithm analysis for breadth first and depth first search. They both have time complexity, big O, of the summation of the number of vertices and the number of edges. For similar reasons, because the outer while loop processes each vertex in the graph that is connected in some way to the starting vertex, and the inner for loop processes the edges. So here is our node processing, and here is our edge processing. The worst case scenario would be that the graph is a complete linear structure, in which case we will be walking through each vertex in the graph. And lastly, down here I have some practice problems using the same UK graph as our previous lesson, L12-1. And with that, I will call it good. I apologize for the excessively long video, but this is a fun one. This is an important one. Breadth first search and depth first search for graphs are very straightforward algorithms using stacks and queues that we have a lot of practice with now.